Alors j'ai le plaisir maintenant d'inviter Ivar Ekeland à nous rejoindre. Comme je l'ai dit ce matin, et je le répète pour ceux qui n'étaient pas ce matin, Ivar Ekeland est en fait un être humain. Il existe vraiment, parce que pour moi, pendant 30 ans, c'était juste un nom sur un livre de mathématiques pour économistes que j'avais beaucoup utilisé quand je faisais des études d'économétrie. Puis j'ai eu le plaisir de découvrir que Ivar Ekeland actually exists.
Hello.
Bienvenue.
So do you.
So do I.
Yeah.
Alors, nous poursuivons cette seconde séance avec des personnalités scientifiques absolument exceptionnelles. Ivar Ekeland est mathématicien, c'est un auteur d'ouvrages sur, vraiment sur le hasard, le chaos, c'est le chaos déterministe. Il a présidé l'université Paris-Dauphine. Alors, ce qui est intéressant, c'est que l'université Paris-Dauphine est née au lendemain de mai 68 avec l'université Vincennes comme deux universités expérimentales. Et Paris-Dauphine fut le foyer expérimental de mathématiciens qui se sont attaqués à des wicked problems liés au monde de l'économie et de la finance. C'était des thèmes qui n'étaient pas travaillés par les mathématiciens. Et au fil des décennies, Paris-Dauphine est devenue une université d'excellence sur les sciences de la décision et de l'organisation. Donc, grand plaisir de vous recevoir avec nous. Ivar Ekeland a aussi diversifié ses thèmes. Il a produit donc des ouvrages sur l'équilibre, les mathématiques du chaos. Et récemment, il s'est investi sur la question du changement climatique. Alors ça, c'est un point important. Il a conceptualisé un cours sur le changement climatique, qui est un cours qui est obligatoire à tous les étudiants de Paris-Dauphine. Il a produit aussi, il est co-auteur d'une bande dessinée, donc très sensibilisé sur la question le challenge du climat et comment exprimer les données scientifiques de manière à conscientiser les individus sur cette question cruciale. Donc aujourd'hui, on poursuit donc cette thématique de la relation à l'environnement, à la nature, avec son exposé. À vous, Ivar.
Merci beaucoup.
Merci. Thank you very much. It's the best part, you get the applause before having done the work. So now let me do the work, and I'm going to ask, so what is this? Yeah, green. So let's see if that works. It works. So I'm going to ask a simple question, but I'm going to set the stage for the question first. So let me set the stage. Look, this is a graph. This graph describes the temperatures for the past 50,000 years. I'm not going into questions about how do you do it and so on. This is scientifically done. It's in a general agreement. These are the temperatures of the past 50,000 years. And you can see the blue line are the mean temperatures. On the left, you see mean temperatures. The yellow line is the carbon dioxide. And what can you say about these lines? First remark, you can see there is some kind of stability. Something changes about 15,000 years ago, but you have some kind of stability. Certainly, you have some kind of stability in the past 10,000 years, right? Now, I'm going to zoom on the past 100 years. Now, I understand that some bright students that's in that class, in that room, in that university, 100 years, how much is it a part of 10,000 years? 1/10? 1/100th. So I'm going to look here at the 100th part on the right. So what do you see? You see here the last part between 1850 to 2020, poof, something happens. It's a shock. Here, this is the last 100 years, and you see something is happening. There's a shock. And remember, this is just the 100th part of the whole graph. Something is happening, mean temperatures are increasing, and it's not It's not uniform. It's in France, it's more. So this is what you call a shock. Now, where does a shock come from? Well, did I miss that one? Yeah. So where does the shock come from? Well, you see, the shock comes from, and you see another graph. Now, these are the CO2 emissions for the past years, and you see that the CO2 emissions have increased. Why do they increase? They increase because we send up, you send up CO2, and this is our global fuel emissions. So there is no problem. We understand the thing, we know where it comes from, you emit carbon, and suddenly, then the CO2 increases. Okay, that's well understood. Now, I'm drawing your attention to this graph because you see the CO2 concentration from pre-industrial levels, 280, has increased to about 400. Now, 400 parts per million, right? That's less than 1,000th. There is very little CO2. Try to figure out how much CO2 there is in this room. Very little. And we have increased, we have doubled, we have increased from 200 parts per million to 400. Not very much, shall we say. In a short time, not very much. Right? It is what we call a nudge. You push something a little bit. So what we have done is, in a short time, push something. So what have we done to whom? Well, we've done that to the Earth, the planetary system. Now, I'm not going to go into details. We all, I think no one in this room would disagree with the idea that the Earth is a complex system. This is complex, whatever your definition of complexity is, this is complex. Biology, physics, this is complex, period. I'm not going to elaborate on that. So the complex system, and what have we done to this complex system, which you don't understand fully? We have pushed it out of equilibrium. I mentioned to you that you had some kind of stability for the past 10,000 years. And now, in the 100th of a time, we've pushed it, we've increased from less 2,000 parts per million to 400 parts per million. It is, and you see this is, we've thrown it out of equilibrium. Now I'm not going to go the details again. What is the equilibrium? The equilibrium relies on the fact that the Earth should send back, gets energy from the sun and has to send it back. If the Earth does not send the energy back to the sun, then what happens? It warms. Yeah, but if temperature constant, it means that it sends back the energy, and now we are perturbing that. We're perturbing the equilibrium. So this is the situation. We have a complex system, which we don't understand fully, and we have, on this system, we have, we perturb the equilibrium, and now here is my question. How does a complex system in equilibrium react when you put a small nudge? Now, remember what I mean. I'm going to stress two things. First thing, I'm saying something very general. I'm a mathematician, and a very strict mathematician. I don't understand the foundations of mathematics. I don't understand biology either, and I don't understand very much about physics, so I understand very little, so I'm going to say general things which will apply to the Earth. I mean, this is the beauty of mathematics, right? I'm not going to say anything particular. I'm going to say something general about systems. And the other thing I'm going to say is, it is a nudge. So my problem is not, if I take a hammer and go hammer this piano, we all understand that something bad will happen. It is not my question. My question is, you have the system which is in equilibrium, and I push it a little bit. Right? I push it. So this is my question. You have a complex system in equilibrium. You push it, you do something to it, not very much. What happens? Now I'm going to give you several answers. First answer, smooth transition. No big deal. Everything happens as before. Just a little increase. No big deal. So you see, you increase from 250 to 500 ppm. Mean temperatures will increase between 3 and 6 degrees C according to the distance you go. And then you say, smooth transition means no big deal. It's a quantitative change. Temperatures will increase. Fine. No, so that's what many people say. We'll have warmer summers. Well, they're already warmer. Perhaps warmer winters also. There will be no big deal. You see, we can adjust to higher temperatures, right? Fine. And there may be some good effects. More carbon dioxide in the atmosphere, better for plants to grow. Warm up certain things, well, you have all the regions of Siberia and so on going to be exploited, so there are some good things that will come out of it. Note, however, that this will already have some bad consequences. Something that's not usually known is that if you have certain combinations of temperature and humidity, they are lethal, meaning you stay out there. If you have 40 degrees C of temperature and 100% humidity, if you stay out there for 4 hours, you die. This already happens in certain countries like Costa Rica. And you find out that the number of days, continuous days, when such things will happen and so on, is going to increase. So, but this is the first answer, smooth transition, no big deal, temperature increases, fine. Small changes all over the place. Small nudge, small change. Very logical. And you see, it's honorable. If you want to win a Nobel Prize, you just argue like that. So let me describe you what the Nobel Prize of Economics in 2018 says. Well, the Nobel Prize in Economics says exactly that. Small nudge, small change. We are going to produce cars, but it's going to be more difficult to produce cars because if it's warmer, then people work. It's difficult for people to work, and you have to install air conditioning and so on, so it's going to be more expensive. And the result is you can be very clever, you can do good mathematics and so on, and the end result is here. You see, optimality, optimal, is at 3 degrees 5 in 2011. You find out that it is optimal to reach 3 degrees 0.5 of warm in 2011, and you get a Nobel Prize. So the question, of course, is, what does optimal mean? And do you believe that? I mean, I know not a single scientist that would agree with the fact that 3 degrees 5 is good in any way. I mean, only economists believe that. But it is the argument, small nudge, small change, and this happens also because you adjust to past data. So that's the first answer. The second answer, very classical, is the system would respond in a qualitative way. And this was pointed out already, I forgot to mention. This is well known in mathematics, and it goes back to Euler. Leonhard Euler, le prince des mathématiciens. So we're going back to, as I remember, to the 18th century. It's called the buckling, le flambage. The buckling is as follows. You have a beam, and you push on the beam. If you push, it's okay. And at some point, the beam, it buckles. You all understand that. So you see now, it's a qualitative change. You can see that it is buckled. It's a qualitative change. It's not quantitative anymore. It's qualitative. This is what we call a bifurcation. So this is a new type of response. You apply to the system, you get a qualitative change. So there's now a qualitative difference. The structure of the system changes. This change is continuous, right? Once you start buckling, the more you buckle, the more you push on it, the more it buckles. And if you stop pushing, you go beyond, then you go back to, right? So it's a continuous change. And it is reversible. So now we have a qualitative change, but it's continuous and it's reversible. How does that apply to climate change? Well, you see here these pictures are taken from the IPCC. And you see, let's look, these are what has been observed up to now. And here you have the changes according to various scenarios. You all know that the Paris Agreement will imply, let me check what the next slide is, yes. The Paris Agreement is that we stick at 2,000 degrees C, or at best 1.5 degree. And you see already that you have some qualitative changes. For instance, if you look at the Arctic, you're beyond 7 degrees. The Arctic is going to be beyond 7 degrees. Well, who can believe that? And now look at here. This will mean some qualitative changes. I'm thinking for some qualitative changes. And for instance, if you look at the next slide, look at this. Precipitations. You're interested in the middle one. So look what happens around here. It happens that you have precipitations inside Africa and the coast, including Morocco, no precipitation. And around the Mediterranean, you go going, and in the Mediterranean, you know, look up at the Mediterranean at 4 degrees, southern France, Algeria, and so on. Then you have the dryness. You have less than 1/2 precipitation. Excuse me, this will be a qualitative change. It's not the same, right? So these are qualitative changes. And in many ways, for instance, you see l'anticyclone des Açores, all these things. All these are going to changes, and fine. If you're interested, and you're students, you should be interested in that, you go to the website of the IPCC. Oh, yeah, here, this is, you go to the website of the IPCC, and the website of the IPCC, you can adjust to get this kind of pictures. There's an interactive atlas. So you go to the website of the IPCC, there's an interactive atlas. If you're interested in a particular part of the world, you plug in the thing, you get the precipitation, and so on and so forth. So this is the second type of response, a qualitative change. Now, perhaps one could say also qualitative. Think, for instance, of the effect of COVID. COVID is a small nudge, but induced a qualitative change. That's the second response. Now there's third response, and everyone has some intellectual heroes. Well, I'm glad to see that I am it for some very indulgent people, but I have my own. Here is René Thom. René Thom is a great mathematician who was born about 100 years ago. He died in 2002. And he was a very nice person, and certainly as a mathematician, my mentor. And part of his mathematical work, he translated it to some practical things which were very successful at the time, which is called catastrophe theory. Now, let me talk to you about catastrophe theory. First of all, let me show you how good I am at computer science, manipulating, making drawings, and so on. I'm fantastic at that. So this is what I do. I draw pictures by hand, and I copy them. So I want you to look at this. I want you to calculate this. You have different shapes, 1, 2, 3, 4, 5, 6, 7, 8, and you move from one to the other continuously. This is what the drawing here says. It says you move, c'est comme un curseur ou un rhéostat. You move, as you move along this curve, you go from 1, 2, 3, 4, 5, 6, 7. Think of it as a kind of button. You can move, if you go around like that, you go from 1 to 7, changing continuously, and you can move back, and you go up, and you can move all the way, you do whatever, and you change the shape. Do you change the shape in a dramatic way? No, it's continuous, right? You all understand this is important, right? You can see that my idea is you move around from 1 to, as you move around, the shape changes, and you can move back and forth, you do whatever you want. Nothing fancy. Clear? Clear. So now let me do something. I'm going to put a little ball on the bottom of number 1. So this is what you get. Now we're going to physics. This is called a potential well. This describes equilibrium. The little ball downstairs is in equilibrium. In physics, it's a potential. It is there. It's not going to move. If you should push it to it, it's just there. Right? So this is a system in equilibrium. And now I move. From 1 to 2, what happens to the ball? Not much. 2 to 3, what happens to the ball? You see, it begins to be suspicious, but those things are happening elsewhere. But the ball doesn't know. You know, these are limited people. They look around them. 3 to 4, things still happen somewhere else, but it's elsewhere. Number 5, things are happening elsewhere, but they're happening elsewhere. And then suddenly here, what happens? Puff! The ball falls down. And this is very interesting. Again, it is general. It's not restricted to that. So this means, so what happened here? Did I make a big change in moving the thing? No. Did something, I made from, when you go here, you see it's very sensitive. If you cross the threshold here, a very small change will induce a very large displacement. So just moving a little bit, you see, the nudge. If the nudge is there, and you see we're increasing regularly the number, the CO2 of the atmosphere, we're moving around the curve like that. It could happen that at some point, the whole system just goes elsewhere. Not nearby. There are two things here. One is there's no warning. You have increased, you have moved continuously, no warning sign. And the other thing is you don't stay close. You move completely elsewhere. Just go somewhere else. Clear to everyone? So this is the first thing. That is what they call the catastrophe. But now let's have some fun. Let's move back. Let's go the thing the other way. Okay? Move back. So I'm moving back. Now I'm putting a little red ball where the other was. And I'm going the other way. So we're here. Now 7 is 1. I'm moving. From where does the red ball go? At point 2, it's still down there. Now, at point 3, the little red ball is not going to climb up. It just stays there. The green ball, here you see the green ball was here, but the red ball is there. There's no going back. It's not going back to original equilibrium, meaning if you reverse the thing, if you take back the carbon from the atmosphere, then it will not go back where it was. The new equilibrium is stable. If you really want the red ball to go back to the equilibrium, you have to go there, up, up, and here it will, and here it will go back. It's very far away, so which means that the threshold here is one way. So, I mean, if you look at that, if you're interested, I think if you want to hear it from René Thom itself, you can look at it in my bande dessinée, in my comic strip, and you will see it. I understand it will be in the library soon, but you see, this is exactly what I say, and here René Thom is explaining to you that at some point it goes down. So that's what the catastrophe is. So again, it's very general about systems. Don't believe that if you make small continuous changes, the system will respond continuously. Not true. A small nudge may cause a catastrophic change. The system goes from one equilibrium to another one, which is far away. The change is irreversible. Oh, I made a mistake. Let's go back. No, no, man. We go back. Now the new equilibrium is stable. And there is hysteresis. Hysteresis means the following thing. Let me go back. If you are in situation 4, I'm telling you, this is the concentration of CO2 in the atmosphere, whichever I tell you, you're in situation 4. You're not going to be able to say in which state the system is, because it depends on past history. Do you come from 7, or do you come from 1? Now, is it relevant to climate change? Well, climatologists have warned us for a long time that they are what they called planetary thresholds. The planetary threshold is a situation where which is extremely sensitive to certain parameters. So these situations. So this situation, for instance, you have them. One is of interest to you. Certainly one is of interest to you. You had the West African monsoon shift, Sahara greening. You noticed that in the raining, that in the slides I showed you, there could be a lot of rain around the Sahara, but there may be a shift in the West African monsoon. There may be a multi-stability in the monsoon cloud. West African monsoon shift, in good language, it means it stops. Period. No more monsoon in West Africa. So what does it mean, a planetary threshold? It's a situation, let me describe it in detail, the one I know better, which is the Atlantic deep water formation. So I'm going to explain exactly what it means. So this is a planetary threshold. Now Europe, so here is Norway, for instance. You see Norway, in Norway over here, the coast is never iced. No ice on the coast. If you go the other way, you see, no ice on the coast of Norway, mild things here, and if you go at the same latitude, you end in Labrador, and you can see the difference. So why is there no ice on the coast of Norway? Because of the Norwegian current. The Norwegian current comes from a North Atlantic current. It is what we call in French the Gulf Stream. And the Gulf Stream is basically taking hot water from the West Indies, les Antilles, and bringing it all the way up north. Fine. So you see, it's an escalator. You take the water here, it's warm, and you bring it here, and it goes along the way. But, I mean, water is incompressible. So it has to come back. How does it come back? It sinks, comes back, and goes up. So it's an escalator. And this is described here. Up, hot. Here, it sinks. And then you have the blue current, which is deep underneath, and goes back. Why does it sink? It sinks, not clearly understood, but it's a question of difference of density. And the density depends on many things, temperature, salinity, and so on, and very sensitive to that. Well, we have no control about these parameters. And you know, when you talk about density of water, you know, it's not going to double anything. You're really talking about very, very small things. And this could stop. And we're now seeing some weakening of that. Has it stopped in the past? Yes. So it is a planetary threshold. This thing could stop because it depends on very small parameters we have no control of. And if it stops, well, no more warming of the Norwegian coast, no more warming of Great Britain, no more warming of the West Europe, and then consequences that you have to figure out. This is a planetary threshold. Now we have, I described to you, 3 answers that a complex system can have to small changes. Has anyone a guess for a 4th answer? Well, the classical answer that all managers know, I mean, this you learn from managing institutions and so on, the unexpected. You just didn't figure out that this would happen. So let me tell you a story. A story coming from Snorri Sturluson, the saga of Harald Haraldsson, 2030, and I took it over in my book on au hasard. So the story is as follows. We are in the year 1000, and the king of Norway and Sweden are fighting over a certain city. And the Vikings at that time, they were civilized people, and instead of fighting, which is now the standard way of doing things, they say, it's not worth killing so many people, let's draw lots. And they decide, we shall throw lots. So the king of Sweden, the king of Norway meet. The king of Sweden throws 2 6s. He says to the king of Norway, thank you, there's no point of your throwing. Come on, says the king of Norway. 2 6s. Okay, very surprised. So we do it again. So the king of Sweden throws 2 6s again. He said, God is with me. Clearly, let's part as friends. I wouldn't want to offend you. Don't throw your dice again. Well, says the king of Norway, there are still 2 6s in the dices, and God, my Lord, would not forsake me in this extremity. He throws the dices, and one of the dice breaks. And when it breaks, it shows a 6 and a 1. So he makes 13, and he wins. This is the unexpected, right? And this happens all the time. This is the thing you had not envisioned. And this happens, right? And in more recent times, you have the famous Rumsfeld classification. Rumsfeld, who was Secretary of State during the Iraq invasion, and not my favorite politician, but he said something very memorable. He says that there are several things when you make decisions. There are things you know. Okay, now a basic fact, which is always pointed out even by Spinoza. Spinoza pointed out explicitly, if you know that you know. Very remarkable. If you know that you know. Fine. But a thing you don't know. Aha. For a thing you don't know is very different. There are things you don't know. Planetary threshold. I'm telling you about things could happen, and I tell you I don't know. Yes, but I know I don't know. But there are things you don't know that you don't know. Right? When you throw that, you don't know that it might break. And it is very important. Some things, you have to realize that there are things that you don't know. It's very ambitious to think you know everything, or that you see, you must understand that things you don't know. And for instance, for me, I think personally, it is impossible to know everything about a living being, and especially about the planet Earth. I just think it's not possible. And there are things that it's not only that you don't know, but you don't know that you don't know them. You just don't know. So I wish to draw your attention in that framework, thing you don't know. Well, this was, is it applicable to climate change? Well, already in 1987, there's a very good, famous article in Nature by someone called Broker, which is called Unpleasant Surprises in the Greenhouse. So it's 87. It was 1 year before the first IPCC report. And you can read the paper. And I'm just pointing out the thing. He's pointing out that there's so much we don't know, and his basic conclusion is, we play Russian roulette with the climate, and no one knows what is in the active chamber of the gun. 1987, published in Nature. And that is a reminder, we don't know. A thing we don't know. So that's the fourth answer. So what is to be done? Well, fortunately, there is much to be done, right? And people here are trying to do a lot. But this is part of the difficulty, you see, because we have a complex problem, and if you expect a simple answer to a complex problem, you're wrong. The answer somehow has to be complex. So it has to be complex. So let's see what the future holds for us. Well, So let me remind you the Paris Agreement says we should limit global warming to 2 degrees C and preferably 1.5 degrees. Okay, I mean, this statement carries as much legitimacy as any statement anyone has made, because it's a consensus, it's voted by the states, and so on. Someone mentioned yesterday about some sincerity of intent. There was an Arabic word for that. Is there sincerity of intent around that? I don't know. But this is as legitimate a statement as anyone has made in this world. And it's supported by growing anxiety in the developed world, especially among the younger generation. So how do we do it? Yeah, that's what I told you. The answer itself has to be complex. So what should we do? So lots of suggestions around. The economist says, let's have a carbon tax. The engineer says, let's have a carbon-free process of production. The economist says, let's customize fertilizers. Municipalities, let's restructure urban transportation. But it is a complex problem. The answer is complex. There is no silver bullet. Not one of them will do. We have to do everything together. And this is what makes the thing exciting. It's exciting because everyone is involved. You see? No single thing will do it. People come to you and say, this will solve our problem. No. It is complex, and it's because of that that it is interesting. You involve everyone. You involve the young, you involve the old, you involve the engineer, you involve the economist, and so on. And you see, my personal point is that future education research should take this new perspective into account. We've been thinking up to now into educating students in math, doing research in math, or in sociology, or whichever. I think we should break these barriers, right? So that everyone, it's a common challenge, and people should be trained to work together, to realize a challenge, and to work together towards solving these problems. And I personally, when at Dauphine, at Dauphine, we've been trying to do that, creating this course for students, which is compulsory for the students, and I am very impressed by what UM6P is doing in that direction as well, and OCP. I mean, this is really, in my mind, the future of education and the future of research. There is this idea that is complex, and everyone has to be together to build this new thing, which is a new world and a new society as well. And so this means change research, train researchers, train students, but also be humble. Be humble. We're not going to know everything. It's just not possible. Think of it. And especially in chaotic times such as that. And so, you know, there are many situations in life when you don't know everything. You know, I meet a stranger, I don't know anything about him, but there are things that you do and that you don't do. There are rules. There are rules of common behavior, of common decency and society, and these rules enable us to work in very uncertain situations with people we don't know. And so these rules are developed in law. This is called the precautionary principle. This is enshrined in the French Constitution, for instance. It basically says, when you don't know, don't do it. And also I believe it's important for personal ethics. You see, the example of Greta Thunberg, I think, is very striking, because if you believe in something, you have to show it. And you can do it in certain institutions. In my own university, for instance, the labs get penalized for using for flying. So I think they're very nice times. I will leave you at that. I will just end by a poetry that you know very well, and that will translate into French. You know that poetry. Personne n'est une île entièrement contenue dans elle-même. Chaque personne est un morceau d'un continent et un morceau du tout. Si une motte de terre a été emportée par la mer, c'est une perte pour l'Europe, comme si c'était un promontoire tout entier. Et si la maison de ton ami est emportée, c'est comme si c'était la tienne. La mort de toute personne me diminue parce que je suis impliqué dans l'humanité. Et c'est pourquoi ne va jamais demander pour qui sonne le glas, il sonne pour toi. Thank you.
Thank you, Professor Ekeland, and thank you for finishing with this beautiful poem by John Donne, Never send for whom the bell tolls, it tolls for thee. I have only one question. You started with the premise that the Earth is more or less in equilibrium, and that give it a nudge, give it a shock, what happens, etc. My question to you is, has actually the Earth ever been in equilibrium? Because you have solar radiation, which has fluctuated, you have the ice ages, you have that strange Milankovitch orbital change in the orbital of the Earth. So basically, the Earth has never really been in equilibrium, but you started with the premise that it is in equilibrium. So,
Yes.
you can use this one, I think.
Yes, this is a question of scale, right? So what I'm pointing, so for instance, it's well known that the astronomy influences the thing, but these work on a scale of like 50,000 years, right? You have other factors. So all equilibria are temporary, especially in this world. You know, my body is in equilibrium. Oh yeah, I mean, I'm in equilibrium because I maintain about 37 degrees. This is fine.
One day this equilibrium will end. So these are temporary, and this is why I began in this way. I'm saying that for the past 10,000 years at last, things have been stable. So this is what I meant at the present time. And many people are attributing to that fact the fact that civilization developed at that time. And things on an unprecedented scale now, things are changing on a scale of 100th. I pointed out that 1 century is 100th of that period. And they're changing very fast. It's really a shock now. So when I talked about equilibrium, I was thinking of a situation that had been around for the past 10,000 years.
Okay, thank you very much. It's now very clear.